Let's record to the cloud. Okay, so today we are going to look at some basic functions. We're going to look at some properties of functions. If you remember before our test, we talked about the idea of a function. A function is something, it's a relation in which each member of the domain, each x value corresponds to a single y value. So we're going to now build on that definition, and we're going to see some fun stuff about functions today. So what we're going to do first is we are going to graph the 6 basic functions that you are going to use for the majority of the rest of our time this semester. We'll get to a point later in the semester where we add a couple new basic functions to our list, but what I need you to do for me, it's going to make your life in this class a lot easier, is to get good at graphing these 6 functions. So even beyond what you do in your homework in my math lab, if you would print out, or I have plenty of graph paper. I'll give you graph paper. I don't want there to be any stumbling block to you taking some time tonight or tomorrow night and practicing graphing from memory these basic functions. That is going to help your success, I promise you. Okay, and I'll remind you, and when we come back on Wednesday, the first thing I'm going to ask you to do is I'm going to ask you to graph the 6 basic functions from memory and to make your best effort at it. Okay, grab one of those sheets right there. Perfect. Okay, so here goes. I'm going to take you through this first time. Let's see if we can zoom in a little more, get this view just a little bit better. Oh no, and I'm not loving this camera. It's not as good as the other classroom's camera. But okay, so first we're going to graph this function f of x equals x squared. It's very cleverly called the squaring function. When we get to chapter 3, we're going to focus very much on this. It's called a quadratic function. You don't need to know that right now. So let me just write here that this is called the squaring function. Grab one of the sheets right here on the desk. So what I'm going to do this first time around is I'm just going to make a table of the relationships just to great, nothing's working. So I'm going to make a table of the relationships. You're going to help me fill in these values, and then we're going to plot the points. And then I'm going to try to just help you remember a nice way to get this stuff down quickly without making a table. So the goal is that we can graph these without always making a table. Grab one of those sheets right there on the desk. All right, so here we go. I'm going to make a little XY table. We talked about tables when we were talking about what functions were. So over on the side, I've got a little. So I'm going to pick the values for you this time. My whole goal in picking the values, there's nothing mysterious here. I'm just picking things that are going to stay on our grid. I've given us a 10 by 10 grid, so I don't want my points to go off that if I can help it. So I'm going to pick these values right here. I'm going to pick 3, and then 2, and then 1, 0, -1, -2, -3. That should give us an acceptable number of points and give us a good looking graph. Now this next bit, I would assume you come into this class with this particular skill, but just in case not, we're going to take each of these values and plug it into the function. So what do I get when I put 3 into my squaring function? What's 3 squared? 9. Perfect. I heard a lot of voices. That makes me happy. How about 2? What's 2 squared? 4. 1 squared? 0 squared? -1 squared? Perfect. -2 squared? And then -3 squared? Excellent. Before I go any further, okay, because I just want to make sure, I know sometimes I make assumptions, but maybe that doesn't include you, and I don't want to leave anybody behind. Does anyone not understand where we got these values right here in the Y column? Because on the test, if you forget the basic shape of this graph, then you should be able to reconstruct it on your own by making a table. I want you to get to the place where you can do this nice and quick and easy, but I understand tests are stressful situations. You might forget. So just make that table. Okay, so just in case anybody's being shy, which I hope you wouldn't, we've taken each of these x values and plugged it in for the x up here and squared it. Now what I'm going to do is I'm going to plot these points, and we're going to see what the squaring function looks like. So when I go to x is 3, then I go up to y is 9. So make a point right here. X is 2, so then the y value is 4, point right here. 1, 1, 0, 0. That's also called the vertex. We'll learn that next chapter. -1, 1, -2, 4, and then -3, 9. There's my points. And then I'm just going to draw. I cannot talk and draw at the same time. So hang on just 1 second. Oh, not too bad. It's early on a Monday. What's happening to my pen? Nothing's working today. Oh, there we go. We're back. I'm going to put some arrows on there so that indicates to everybody that this is a function. It keeps going. That's not a line. This is curved. It's called a parabola. When you go to the water fountain and the water comes out in the form of parabola. Satellite dishes, they're in the form of a parabola. There's a lot of cool properties that make them useful. Okay, so I'm just trying to indicate to you that that is curved at the bottom. It does not come down to a V, although my graph might make you think it comes down to a V because I'm not great at drawing. Are we good? Do we see the shape of the parabola? Remember, one of your homework assignments is to print out a sheet of graph paper or ask me for a sheet of graph paper before you go and to redraw these as best as you can from memory. Getting familiar with these is one of your homework assignments. That's the first of our 6 basic graphs. We're going to move to the next one. We're sliding by. We're going to come back and we'll come back. We're going to talk about some properties of these different things. This next one, does anyone know what these bars mean? Yeah, absolute value. You may or may not have seen that before. Absolute value. This is another function we will talk about in greater detail later in the class. What the absolute value does is it just basically takes any number and makes it positive. So for instance, I'm just going to flip over just in case it's been a while or you haven't seen absolute value. Just a couple of quick examples. If I said, what's the absolute value of -9? Then you would tell me the absolute value of -9 is 9. Great. If I asked you what the absolute value of 15 is, you would say that that is 15. Okay, another way to think about absolute value is it's just how many hops on the number line you would count to get to a particular number. Okay, so it takes a negative number and makes it positive. It takes a positive number and it stays positive. The result of an absolute value is always a positive number. And then let me just make sure I've covered all of our bases here. The absolute value of 0 is going to be perfect. Well said. Love it. Okay, so if that's about as familiar at this point in time as you need to be with the absolute value. So what we're going to do is we're going to take that little bit of knowledge now and we are going to graph the absolute value. Again, I'm going to use a table here this first time around, and we'll hopefully be able to recreate it from memory as we get more and more used to it. So here's my XY table. Again, the only thing I'm doing is I'm picking X values that are going to stay on my grid. There's nothing mysterious or secret about what I'm picking. So just for fun, I'm going to pick 5, I'm going to pick 2, 0, -1, -4, -6, since I had a little room. Once again, I'm now going to take each of those X values and I'm going to take them and I'm going to plug them into the function up here. So once again, if your question is where in the world is he getting these Y values, that is a fantastic question. You should always ask your questions when you have them. So help me out. What's the absolute value of 5? 5, perfect. What's the absolute value of 2? Absolute value of 0, -1, -4. An absolute value of -6. Excellent. Great job. I'm just repeating things because I'm hoping it'll sink in and you'll remember it when we get to things like the test. But again, my hope is you'll remember the shape of these and be able to produce them quickly, because when we get to the next when we get to a section later in this chapter, we're going to be doing things with these functions. But again, on the test, you can always just recreate this table. It's never going to change. And so now I'm going to plot these points. I'm going to go over 5 and up 5. I'm going to over 2, up 2, 0, 0, -1, up 1, -4, up 4, and last but not least, -6 and up 6. And the absolute value function forms a nice V. These are straight lines. I missed a dot there, sorry. There we go. The absolute value is looks like a V. I know it seems like we're just doing some fun artwork here, but this is super important for your future. So if you have any question about where these points are coming from, where the shapes are coming from, please, 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 I beg you, ask that question. Can I move on? Is everyone good? Caught up? We good to go? All right, I'm going to move to the next function down here at the bottom left. This is the cubic function, okay, because it's x cubed. So not really a fancy name for it. Again, my choice of values is simply predicated on the size of the grid that I've given you. If we had bigger grids, we could graph or we could put in different values. So I'm going to put in the values 2 and 1 and 0, -1 and -2. What do I get when I cube 2? 2 cubed is 8. Perfect. 2 times 2 times 2 is 8. How about 1 cubed? What's 1 cubed? 1. What's 0 cubed? Yes, indeed. How about -1 cubed? What do I get? -1. Okay, a negative times a negative is a +1, times that third negative is going to give me a -1. Okay, so important to get that sign right. In case I know it's Monday morning, we're thinking quick. And then -2, what do I get when I cube that? -8, perfection, well done. So now I will graph these 5 points and we'll see what the shape is. So I go over 2, I'm going to go up 8. So right there, over 1 and up 1, 0, 0, -1 down 1, -2 down 8. So the cubic function, it looks kind of like a plane propeller. Oh, I totally missed a point. I'll get better, I promise. If you ever take calculus, I know some of you, that's where you're going. Some of you, this is your last math class ever, and you're going to rejoice the last day of class after the final exam. But all sorts of fun stuff happens around the origin of the cubic function. So it's a really interesting function, even though it looks kind of plain right here. So that is our cubic function so far. Questions, comments, concerns before we hit the last function on this page? And then before we flip the page, we're going to review something that we talked about functions last time, just to make sure that we're all good. All right, the last one is the square root function. So my square root function, if you remember our properties of square roots, the square root function is the first one of our functions that I'm going to pick that I have to pick certain x values. Okay, we haven't had any problems. I haven't mentioned this up to this point, but I've been able to use any x value I wanted for the other 3. But now this one, I can't. What x values can I not plug in when I'm graphing into the square root? Negatives. Okay, we get complex numbers if you remember your intermediate algebra, but there's no for a complex number on my graph. So we're going to avoid them right now. So what that means is the first x value that I'm going to pick is going to be 0. And then my choice of x values, I am fundamentally lazy when it comes to math. I don't want to do more work than I need to. So I'm going to pick numbers that have a good square root. So I avoid decimals and simplifying. I don't want to do any of that. So numbers that have a nice square root, 1, 4, 9. I'd use 16, I'd use 25, but again, I'm just limited by my graph size. So again, as you're writing those down, if you're like, why in the world did the Perkster pick those values? It's because I picked things that I can take the square root of in my head and ignore decimals. Okay, we're going to get very nice values here. So what's the square root of 0? What's the square root of 1? Square root of 4? 2, thank you. Square root of 9, perfect. Remember the square root, that's the operation. It's asking you what number times itself gives you what we started with. So 3 times 3 gives me 9, 2 times 2 gives me 4, 1 times 1 gives me 1, same thing for 0. So now I will graph this function. So my first point is 0, 0 right here at the origin. Then I've got 1, 1, then 4, 2, then I've got 9 and 3. And what this is, what it looks like, what it is, it's a parabola that's been cut in half and is now laying sideways. And there's a reason for that relationship. We'll talk about that later on in the class. I think when we get to chapter 4, we talk about the reason for that relationship. All right, before we flip the page, I just want to remind us of something we talked about last time, okay, because I don't want to have to go, just for a couple of these functions, we're going to do the following. So for the squaring function, this will be my example. I just want to real quick write down what the domain and what the range are. This was something on the test. This is something we talked about last week. Just something, a point of review. So the domain, what does the domain refer to? The x values. So lower bound, what's the furthest left this graph is going to go? Negative what? Not -3, because I got this arrow. Okay, -3 is only as far on the graph as we went, but remember our graph is just limited by the size. If I had a bigger piece of paper, I'd have a bigger graph. So how far to the left is this ultimately going to go? -infinity, yes. I can put in any x value in the negative direction as I want. There's no limitation on what I can square. And how about right? How far to the right is this graph going to go? Regular infinity, yes. So I can go as far to the right as I want to. That just means I can plug in any value into the squaring function that I can possibly think of. There's no limitations. Now this one does have a limitation on the range. That I am limited on what I'm getting out of this. What's the lowest? What's the furthest down this function goes? Perfect. What's the highest this function's going to go? Excellent work. Good job. And then we always put a parenthesis at infinity. This time, since it does go through the y value 0, I'm going to put a bracket on this side to indicate the equality. So I would like you just to do me a favor for the two functions on the bottom, the cubic function and the square root function. If you would just real quick write down what the domain and the range are of those two. I just want to make sure that we have that. And then that'll be probably the last we talk. No, I think we'll talk about domain and range again a little later, but not for our 6 basic functions. So what I'm hoping you wrote down for the cubic function is that the domain of this is from -infinity to infinity. I can cube anything. There is no number that I cannot plug in here and multiply times itself 3 times. Okay, so I can choose anything from -infinity to infinity. How about the range? How far down does this go? -infinity. How far up? Perfect. Well done. The square root function, in all honesty, is the only one of these 4 that's really interesting to talk about the domain and the range. So my domain for this, according to my graph and what we talked about as far as graphing square roots of negative numbers, how far left can I go? 0. How far right is this graph going to go? Yeah, it's flying to infinity. So again, I go through that point 0. So I'm going to put a bracket right there and be done with it. How about the range? What's the furthest down? What's the lowest y value? Again, 0. What is the biggest y value going to be? Yeah, it's growing slowly, but it'll eventually get to infinity at some point in the future. So we'll do that. Before I flip the page, questions, comments, concerns? Anything bothering you so far? Okie dokie. So we'll flip to the next page. Now I've got a cube root function. So like the square root, the cube root is saying what number times itself 3 times is going to give you the input. Okay, so that's what the cube root. I'll get it right one of these times. So again, my choices in x values are simply going to be things that have a nice cube root that I can do in my head or with my calculator, but I'm not going to get decimals. My goal is to avoid anything like that. So I'm going to plug in 8, I'm going to plug in 1, 0, -1, and -8. What times itself 3 times gives you 8? 2. 2 times 2 times 2 is 8. Wonderful. What times itself gives you 1? 1. What times itself 3 times gives you 0? I know that's what you meant. What times itself 3 times gives you -1? There you go. Good. -1. And then what times itself 3 times gives you -8? And again, I could plot more, but the cube roots, just like the cubic function on the previous page, these values get big real quick. Okay, so like I could put in 27 and -27. They have a nice cube root, but I've given you just a small grid. So I'm just reminding you, as far as when it comes to domain and range, the only limit is the kind of the screen that we have here. So let's go ahead and plot these. So 8 gives me a value of 2, 1 gives me a value of 1, 0, 0, -1, -1, and then -8 and -2. And there's my graph right there. It looks very similar to the cubic function on the previous page, just going left and right instead of up and down. And again, we'll talk about why that relationship is true, because there's a reason they look the same when we get later in the class. Our last of the 6 basic functions that you need to practice and be able to reproduce, because this is what's going to occupy the majority of our time for the rest of this semester. This is called the identity function. If you took intermediate algebra here at Polk State or probably anywhere else, then you're familiar with this. This is just going to give us a line. So, pardon me, we will go ahead and make our table. Maybe you're already graphing it because you remember slope and y-intercept and you're already done. That's fine too. The identity function is called that because whatever you plug in is what you get out. Okay, it's not super interesting. So I'm going to plug in 7. I'm going to plug in 2, 0, -1, -5, just for some different values that we haven't used before. So looking at my function up here just says, okay, whatever the x value is that I plug in, that's going to be the x value that I get out. Okay, so that's what this notation is telling me. So when I plug in the value 7, I'm going to get 7. Yeah, when I plug in 2, I'm going to get 2, 0, -1, -5. So I'm going to plot these points, 7 and 7, 2 and 2, 0 and 0, -1 and -1, and -5 and -5. I don't have a straight edge with me, so you're going to have to pardon me. But not too bad of a line for a Monday freehand. There we go. Okay, so I have some other things about functions we're going to talk about in this section, but I wanted to get that out of the way first, talk about the 6 basic functions. So this is the last time I'm going to say this today. Well, maybe I'll say it at the end. At least one time between now and when we get back on Wednesday, practice doing these the best you can from memory or making the table. Very first thing I'm going to ask you to do Wednesday when we come in is to do that for me. Okay, so pretend like you're going to have a quiz. Okay, it's not a quiz, but let's go ahead and pretend. They are important, and not all, but like 80% of the problems we do in the next 3 chapters are going to be based on these graphs right here. All right, so now what are some properties of functions? Since we know what a function is from the previous unit, we've looked at 6 basic functions. Well, the first thing that I'm going to mention to you, the first property of functions is this idea of continuity. So a function is continuous over an interval if, now this isn't the mathematical definition, you'd need a little bit of calculus in order to understand the mathematical definition, and that's not my assumption. So I'm just going to tell you how you can observe a graph and tell if it's continuous. A function is continuous over an interval if you can trace it without lifting your pencil. Whoops. Yeah, there it is. If you can trace it without lifting your pencil or finger or crayon or whatever you're writing with. Everybody got that written down? So if a function is continuous over a particular interval, if you can trace it without lifting your pencil. So let's look at example 1. So is this, let me form the question. Is this continuous for all real numbers? Meaning, do I ever have to lift my pencil or pen when I'm tracing this? Yeah, right here, right? There's a gap. What that's called right here, this is called a point of discontinuity. Fun word. Unfortunately, then what I can't say is that this is continuous on the whole number line, negative infinity to infinity, but we can break it down into intervals it is continuous on. So a question that you will be asked on the homework, question I'm going to ask you on the test, I promise, okay, is where is this continuous? Okay, on what intervals is this continuous? Here is something I'm going to repeat a bunch because on our first test, there were some people that did not get this part, and I understand it's a very common mistake, the first unit in this class. But when we talk about this, when we talk about continuous, what we're talking about is the x values that produce the continuous y values. When we talked about inequalities and solving equations, on the first unit, we talked about the x values that produce those y values. So the intervals that I'm looking for are intervals on the x-axis. I'm going to trace this. So this right here, where my pen is going, I am continuous up until I get to the very end right here, where I get to the edge of the cliff. So what I want to do is I want to describe what is the interval on the x-axis that produces these y values that my pen is tracing. Well, I've got an arrow down here. Please note that. That means how far to the left? How far left is this interval? Negative infinity. Well said. Excellent. Where does this stop being continuous? What x value does this stop being continuous at? Yeah, this right here. I'm just going to put a little mark right here so everybody can see it. Right here at the x value 2. Now, this is not a distinction that this is not a detail that I will mark you wrong on in this class in college algebra. If we were in pre-calculus, I'd be a little more stringent on this. For continuous, you use parentheses always. Okay, but on a technicality, if we talked about the mathematical reason, you'd have a little more understanding. But like I said, if you put a bracket here on the test, I'm not going to mark that wrong on continuous. Okay, but I'm going to put a parenthesis there. I'm going to put a comma. We're not using, I know somebody asked one of our earlier classes, am I going to union these together? We do that for domain and range. We'll talk about that later. For continuous, I'm looking at separate intervals. These things are not related to each other. So I'm separating it with a comma. I'm just making a list here. So the next interval. Well, the next interval, here's the next part of this graph where it's continuous, right up here, where I'm tracing now. Where does that interval start on the x-axis? Starts at 2. And then where does that interval end? Notice the arrow. Forever, infinity, yes. Well said. There's my 2 intervals that this graph is continuous on. I'd like you to do the same thing for example 2. I would just like you to note the intervals on which that function is continuous, please. Exactly. You're right. There's going to be 3 intervals this time. The point to remember, I wish I did that intentionally. Sorry. The point to remember here is that we are giving the intervals on the x-axis that produce these continuous intervals. Okay, so if you've got slightly different numbers, you might be looking at the y-axis. So we are giving the intervals along the x-axis that are producing. So this first interval that it's continuous that I'm tracing starts at -infinity because of the arrow. If there was a dot down here, we'd have a different result. So -infinity. And then what x value do I stop at? Right here at -4. Yes. If you put -3, then you are looking at the y values. Okay, so we are looking at the x values. If you did it, don't beat yourself up. Okay, I'm repeating this a lot because that is a very normal thing to overcome. The next one. What's the lower bound and upper bound of this interval right here? Perfect. -4 to 3. Excellent. And then finally, this last interval, this last piece that's continuous right here, goes from 3 to infinity. Once again, if you started this last one at 1, you're looking at the y values. We're always giving the x values. Before we turn to page 3, I'm going to go back to page 1 real quick. Just for my squaring function, since I'm picking on this, if I asked you where this function was continuous. I know what you mean. What'd you say? 2. Perfect. Yeah, and you said yes because we never have to lift up our pen. There's nowhere that this is discontinuous. Does that seem reasonable? So if I asked you what interval is this one continuous on, you would say from -infinity to, that's a terrible infinity. You paid good money for this class. Okay, so from -infinity to +infinity would be the interval of continuity there. Because there's never any place that you have to lift up your pen or pencil or finger when you are tracing it. Not going to write it down, and you can if you want to. If I looked at the absolute value function, what's this continuous on? -infinity to +infinity. Don't worry that this comes down to a v. In graphs, that's called a cusp. You don't need to know that. That's just extra knowledge because I want you to get your money's worth today. Okay, so you never have to lift your pen up, so that's -infinity to +infinity here. In fact, the only one on the front that's not is my square root. If I asked you where the square root was continuous, what interval would you say? Yeah, 0 to infinity. It doesn't even exist anywhere else. There we go. Questions, comments, concerns? Fun stuff with functions. Yes. What a great day. Let's do one more of these continuous ones because I'm just showing you different looks at different types of graphs that you're going to see. So when I look at example 3, is this continuous everywhere? Okay, I see why you're saying that, and that's why we're looking at this. This right here is a hole in the graph. And I know you're thinking, hey, I could go and then I could go around the edge of the hole like it's the Grand Canyon and keep going, but that's not what this graph is meaning. Okay, so I'm just going to let you know that this right here, this is representing a hole in the graph. Okay, those rounded parts are not part of the graph. That's just me drawing the gap. Okay, because if I did just draw a gap with my pen and then didn't do the little round part, you would wonder how big is that gap. So this is just the way that we notate it. So for a graph like this, if we asked about continuity, well, then we would say negative infinity. Now, where is that point of discontinuity? What is the x value that I have to lift up my pen at? 5, yes. And then once I jump over that little gap there, it's continuous again from 5 to infinity. Yes.
Will there ever be a situation where, let's say there's 2 gaps or 2 points where the line stops, but it's on the same?
Okay, so here's the question that is being asked. It is a beautiful and fantastic question. If I'm understanding it, let me know if I'm understanding. Forget that this. Okay, I just want the graph here. So the question, the way I'm understanding it, is what happens if something like that? Is that what you're meaning, where they overlap?
Kind of, but like on the same exact line.
Oh, okay. Well, first thing, to answer this question, there's a problem with this, though. We wouldn't be considering this because is this one a function? No, because if way I understood overlap, notice it wouldn't pass the vertical line test, so it's not a function. Okay, let me try again. If I don't get it this time, you're going to draw the graph for me, and then we'll see if I can answer the question. So are you meaning, would I have 2 gaps like that on the same graph? Yeah. Okay, so this situation would be similar to the second example we did. How many intervals now am I going to have since I have these 2 points of discontinuity? Yeah, there's going to be 3 intervals. So the first interval would be negative infinity to whatever this x value was. And then the middle interval would be from that x value to this one. And then the final one would be from here on out.
It's not quite right.
Okay.
So it's that exact line, but there's only two points basically.
Draw your question. Okay.
So those brackets are showing 2 separate. But since you explained the first one, because it wouldn't be a function.
Yeah, this wouldn't be a function.
Yeah.
So I'm not going to put it up there. We can talk about more after class, but I don't want to go too far down this rabbit trail and inadvertently confuse anybody. Okay, so we can talk about this, you and me, after. Are we good so far with what we've got? Okay, the next thing that we're going to talk about with functions, this is down at the bottom of page 3. We've skipped a couple graphs. We'll come back to them. So we've talked about a function. We've talked about our basic functions. The first attribute of functions I mentioned was continuity. The second attribute of functions that we're talking about here is increasing, decreasing, or constant. So I'm going to write up the mathematical definition. I'm going to try to show you what that means on a graph so that you can visualize what's happening here. So we would say that a function f increases on an interval if the following is true. If for x1 less than x2, all that means, that's fancy mathematical lingo from I'm reading the number line from left to right. Okay, as I'm going, each first x value is less than the next one. And I'm going to show you this on a graph, but that's just the fancy math lingo to say I'm going from left to right, like we would ordinarily read a sentence. Okay, left to right. So for x1 less than x2, then what happens if I have something that's increasing is the function value at x1 is less than the function value at x2. What does the word increasing mean? Okay, adding, yes. Here's what I'm looking for. Bad question. When I get bad answers, or not bad answers, but when I get answers that are not more clarifying, it's because I've asked a bad question. Increasing just means to get bigger, right? When your paycheck increases, hopefully, it means that it's getting larger. So I just asked that because I want to look at this graph that is in example 5. There is a place on this graph where the y values are increasing, meaning they're getting larger. Okay, so is it this interval, interval 1? Is it the middle interval, interval 2? Or is it the last interval, interval 3? 1, 2, or 3 that the y values are getting larger? Okay, interval 1. Okay, so what I want to do is I just want to show you what this definition that I just wrote down is actually saying to hopefully make you feel a little better about it. So here is x1, and then over here, this is x2. So x1 is less than x2. That was the part of the definition I told you, just means we're going from left to right on the number line. You tracking with me so far? Yeah. x1 is less than x2. Well, let's look at the corresponding function values, because you told me just by observing, just by noticing that increasing means to get larger, you said this was the increasing part of the graph. So let me go down to this function value. This right here is the function value at x1. And then when I make my dotted line here, this is the function value at x2. What's the relationship between those two function values? The function value at x1 is what compared to the function value at x2? It's less than. Okay, it's further down the y-axis. And that's what the mathematical definition is telling us about increasing, that when I have my x1 to the left or lower than x2, then my function value at x1 is going to be lower than the function value at x2. And that was just the fancy math way to write it right here. I just want you to be, I know some of you are going to pre-calculus, so I just want some of you to get used to seeing things written out mathematically, because you're going to see an awful lot of that when you get there, and I don't want to leave you hanging here. That's part of my job. Okay, well, what I'm interested in then is I want to know what is the interval that this graph is increasing on. This is the x value right here, and that is 1, 2, 3, 4. So you are completely 100% right. It's increasing from negative infinity to negative 4. Here's my phrase of the day that I'm going to repeat. You're always giving the x intervals on that produce these y relationships. So you told me the y values are increasing here. So we gave the x values that produce those. Okay, there's no other increasing intervals, so I'm going to move on to the next one. We can talk about the function decreasing. The function f decreases on an interval if for x1 less than x2. That's just the exact same thing that's written right above it. The only thing that changes this time is for decreasing. My function value at x1 now is going to be greater than the function value at x2. Means as I go from left to right, the function values are going to keep dropping down. So for the example that I was just doing, example 5, which interval is the decreasing interval here? The left one, the middle one, or the right one? The middle one, yes. As I trace this, notice these y values are decreasing. So as I go from my smaller x values to my larger x values, the y values go down. Where does this graph start decreasing? -4, here is the x value right here. It's actually where we stopped increasing. Where does this graph stop decreasing? Okay. Right here, I'm just going to put a little mark there at 5, and you are 100% right to 5. And last but not least, we can say that a function is constant on an interval if for the x1 less than x2. So again, as I'm reading from left to right on the number line, then this time, if it's constant, that means that the y values never change. Okay, they're equal. The function value at x1 is equal to the function value at x2. My example 5 had one of each, just so that we could talk about each of them. So since we've already talked about the left and the middle interval, your guess would be that it's constant on this right interval, and you would be right. This is where the y values do not change. The y's are always equal. And so where does that start happening? 5, and then because of the arrow, the upper end of this interval is, you are 100% great. Wonderful. Well done. What I would like you to do, example 6. The question is this: list the interval or intervals, if there's more than one, where this function is increasing, decreasing, and constant. You can have more than one interval, or you can have no interval. Yeah. Great question. I'm just going to move from the left side of this graph to the right, and we're going to talk about each interval as they come, and we're going to see what's happening. So as I'm starting on the left side of this graph over here, what is this graph? Is this increasing, decreasing, or constant on the left side? It's constant. So what's the lower bound of where it's constant? Okay, -infinity. And then where does it stop being constant? Yep, at this x value right here, -5. Remember, we are giving the x values that produce those constant y values. Then what happens to the graph at that point? It's increasing now. We're climbing the hill as we go from left to right. And so we climb the hill starting where? -5, and where do we stop climbing the hill? Yep, we're at the top of the hill at -2. I just want to pause. Is anyone confused about why it's a -5 and a -2 inside the parentheses there? Those are the x values that are producing those increasing y values. I just want to get you used to seeing that. I don't want any errors on that. Now, what does the graph do? Yeah, we're sliding down the hill now. And so it starts, I think you would say at -2. Where does it stop sliding down the hill? +1. And then the last thing this graph does, it's constant once again. That is fantastic. And so it starts being constant again at 1. And then since there's an arrow, if I put a dot there, it would stop and we'd have an upper bound. But since it's an arrow, we keep going. Excellent. You can have more than one interval that a function does this. You can have none. A function doesn't have to be increasing or decreasing. In fact, let's look up at example 4. Same question. Increasing, decreasing, constant, example 4. Again, I'm just going to go from the left part of this graph to the right. Starting at the left to right, what does the graph start out doing? Decreasing, that is exactly right. So it's decreasing from -infinity, and this x value right here is -6. And then it starts increasing, yes, from -6 and then to 0. And then last but not least, it starts decreasing again. So it decreases from 0 to infinity. Notice there is no interval where it's constant, so I leave that blank. We don't have to have everything. That's why I wanted to do that example. We've got one more thing we're going to talk about, but before we do that, we're going to go back to page 1. Just to go back to our basic functions and real quick, just remind ourselves of what's going on with them. So absolute value on the first page, same question. Where is it increasing, decreasing, and constant? Just absolute value. We're going to go one at a time. I got one more we're going to do after that, and then we'll hit our last topic. Again, I'm going to start at the left of this. I'm going to go to the right. So when I start to the left, what is the absolute value graph doing first? It's decreasing. Yes, it is. It's decreasing. Starts at -infinity, and right here at the cusp, that's 0, and it stops decreasing right there. And then it immediately turns and increases. Yes, from 0 to infinity. Again, it's not constant anywhere. One more example. Do the same thing for the cubic function. In fact, you might just answer the question, what is it doing and where? But you can write down increasing, decreasing, and constant. When I start at the left side of this graph and I go to the right, what is the cubic function always doing? It's always increasing. It never stops increasing. So it doesn't do anything else. So the answer to this is increasing. And the interval that it's increasing on is, what's the lower bound of that interval? Negative infinity, and that's the upper bound? Yeah, exactly. If it never does anything else, that's negative infinity to positive infinity. Well done. Well said. We have our basic functions today, and then we reviewed domain and range. We talked about continuous, increasing, decreasing, and constant. Anything you need me to clarify right now? We've got one more thing to do. Last page of our little packet here, page 4. What does it mean for something to be symmetric? What's the word symmetric mean? Somebody said it. Same on both sides. Perfect. Okay, so like our faces, you painfully cut us in half, we'd be essentially same on both sides. That's symmetric. Okay, so symmetric, there's two types of symmetry, which is just the different form of the word. There's two types of symmetry in this class that we're going to deal with respect to functions. Okay, the first is symmetric with respect to the y-axis. The more common way I will refer to that is what's called an even function. Let's flip to page 1. We've got 4 functions on page 1. 2 of them are symmetric with respect to the y-axis. 2 of them are even functions, meaning if the y-axis was the middle of a greeting card and we folded it on the y-axis, we'd have the same thing on both sides. What are the 2 functions on the first page that are even? Okay, the squaring function is even. That is indeed true. It's the same thing on both sides of the y-axis. And the absolute value is an even function. It's the same thing on both sides of the y-axis there. Reason I point that out is I'm going to write down the mathematical definition of even, and then we're going to come back to those 2 graphs. I'll probably use the absolute value since it's wider and I have a little more room to write, because I want to show you what this mathematical definition is saying. So I'll be back here, put your finger there, but something is symmetric with respect to the y-axis if the following condition holds. If f of negative x is equal to f of x. I'm going to explain that a little more after you write it down. What this is saying is if I go in the negative direction x units and I go in the positive direction x units, if I'm going the same distance in both directions, then what I should get is the same y value. Okay, I should get that's why it's an f with whatever inside. I should get the same y value. Let me point out what this definition is saying on the absolute value graph. So here is -4, and here is +4. I've gone the same distance in the negative and the positive direction. So if it's even, if it's the same thing on both sides of the y-axis, then I should have the same exact y value. So let's just ... There we go. ... There we go. And notice I am at the same exact y value right there. And you can do that for any x value. So if I went back -9 and I went +9, then for both of those, if I had extended the graph enough, I should get the same y value. And that's what the definition of even is saying. You with me? I know these mathematical definitions, they can be taxing. I totally get it. Well, the reason I mention this is because we're not always going to have the graph, and we might want to know if something's even. So for instance, I'm going to do f of x equals x squared. A question that you're going to be asked on your homework, and you're going to be asked this on the test, is to show if this is even, or to spoil it, odd or neither. The next type of function we're going to talk about is odd. Okay, so the question is this an even function, an odd function, or neither? And so I'm going to show you the algebraic way to show this. Okay, no matter what. Okay, so I am going to show that this is even. So you always start here. Okay. Every time you're asked this question, this is always the first thing you write down every single time. You're going to start with f of negative x. What I'm going to do is I'm going to plug a negative x into my function. I'm going to see what happens. Now this is a nice simple function because it's our first example. We're going to have other examples in just a minute, but here we go. So I'm going to say this is equal to. So what I'm doing is I'm plugging a negative x back into this function right here. And so that means I've got negative x squared. Mathematically, this is arithmetic. What happens when I square a negative? A negative times a negative becomes, right, I'm just going to write this over on the side just in case anybody forgets this later. A negative x times a negative x is going to be a positive x squared. And so I'm just going to write x squared here. And then here's where I'm going to end. X squared is my original function. So I'm just going to say, oh, that's my original function. And that there is the definition of what it means to be even. You start with f of negative x and you end with f of x. That's this relationship over here. So we have just demonstrated, I know we don't like the word prove, it's scary, but we've just demonstrated that x squared is an even function. The other type of symmetry that we have is something symmetric with respect to the origin. This is called an odd function. What I'm going to do is I'm going to tell you what to look for an odd function, and then we'll see that on one of our basic graphs, and then I'll show you the algebra, and then we're just about done for the day. Okay, so symmetric with respect to the origin means if I put my pen at the origin and I twist the graph all the way 180 degrees, I'm going to get the same graph. So for instance, on page 2, here's my cube root graph. I'm just going to tell you up front, the cube root graph is an odd function. It's symmetric with respect to the origin. And here's why. I'm going to put the tip of my pen, hopefully you can see this, right here at the origin. And now I'm going to spin the graph 180 degrees. Is that the same graph that I started with? Does it look the same? Yes, it's the same exact shape. So of our 6 basic functions, there are 2 more that are odd. There are 2 more that if you spin along the origin, you'll get the same thing. So real quick, see if you can identify which 2, write down the letter O or the word odd next to them, and then we'll compare notes in just a second. There are 2 more. What's one of the 2 more? Okay, the cubic function. Yes, the cubic function is indeed odd. So if you took your paper and you spun it for the cubic function, you're going to end up with the same shape function. And what's the other one that is odd? The identity. Yes, the identity. My line, that is an odd function. All right, home stretch. And then I know that you want your tests. I haven't forgotten them. They're sitting right here in front of me. So the algebra for symmetric with respect to the origin is f of negative x is equal to. So it starts out the same way, but notice instead of getting the exact same thing, when I spun it 180 degrees, I get the exact opposite value. So I'm going to go to my identity function. I'm going to show you why this is, and then we've got a couple of examples and we'll be done for the day. So here's my identity function. What this means is if I go out, if this is my x value, and then out here in equal distance, this is my negative x. Notice the y values are not identical this time. The y values are opposites. This one is above the y-axis. This one is below the y-axis. That's what it means for something to be odd. All right, so end result. We each got time for one of these. We'll save the third one. You can do it for homework or we'll do it together. This will be this last problem right here will be where we start class next time. So if you want to do that problem as homework and we can compare notes, that's great. What I'm going to do for this example is I'm going to determine analytically, that's the key here. I'm going to determine out analytically if 8x to the fourth minus 3x squared is even, odd, or neither. So what I'm going to do is I'm going to start off with this statement, f of negative x. And I am going to determine, according to my definitions, do I end up with what I started with, f of x, or do I end up with the exact opposite of what I started with? So here goes. So I'm going to have 8, and then I'm going to put negative x in there and raise it to the fourth power, and then minus 3, and have negative x in there raised to the second power. I'm going to ask you the same sort of question we just asked a moment ago with the x squared. What happens if I take a negative number and multiply it by itself 4 times? It becomes positive. Okay? Negative times negative times negative times negative becomes a positive x to the fourth. How about, we already said this, but I'm going to ask you again, a negative number, raise it to the second power. Becomes, yeah, so the sign doesn't change, so I'm going to have minus 3x squared here. How does that compare to my original function? Is that the same thing? Is that the opposite? Or is it neither of those two things? It's the exact same thing. So this is f of x. And so that means this is an even function. Some of you might be saying, hey, Perkster, it's an even function and the powers are even. And that's part of the relationship, yes. But I want you to learn how to do this algebraically because there are functions that don't have powers, like the absolute value and things like that, that you need to know this relationship for. So your last problem of the day is I want you to do your best. I know that this is your first time doing it. Do your best to determine if 6x to the third minus 9x is an even function, an odd function, or neither of those two things. The statement you're always going to start with every time you're asked to do this is f with the negative x plugged in. I want to see how this function responds when I plug in my negative x. So I've got 6 and negative x cubed minus 9 negative x. Well, negative x to the third power. What happens to a negative when I multiply it by itself 3 times? Stays negative. So I've demonstrated that here on the side. Negative x cubed is negative x times negative x times negative x. Well, the x times x is x cubed, and the negative times negative times negative is negative. So what you've done is the negative now comes outside of the parentheses because a negative multiplied 3 times is negative. So this first term on my problem is going to become negative 6x to the third. Now I don't have a power on the second term, so a negative 9 times a negative x, this is just introductory algebra right here. What's a negative times a negative going to be? A positive, so that's positive 9x. So how does this compare to the original? Is this the same thing as the original? Is it the exact opposite, or is it neither of those things? It's the opposite. Notice, my first term was 6x cubed, and now it's negative 6x cubed. My first term here, or my second term was negative 9x, now it's positive. So this is the exact opposite of what I started with, and that's the definition of odd. So spoilers, if you do the last problem for homework, and we'll do it together next time, you are going to get neither for that one. That's the result. So give it a try, and we'll see how you did next time. All right, so I'm going to shut down the recording.